What if the very fabric of reality isn't as smooth and solid as it seems? What if, at the tiniest scales imaginable, the universe is a bubbling, frothy sea of chaos? This isn't science fiction, it's the mind-bending world of quantum foam, a concept so strange and fascinating that it challenges everything we think we know about space, time, and the nature of existence itself. Quantum foam is the idea that space-time, the stage on which the universe plays out, isn't perfectly smooth. Instead, at the smallest scales, think a billionth of a billionth of a billionth of a meter. It's a turbulent, ever-changing landscape. Imagine a calm ocean suddenly zoomed in to reveal a stormy, churning surface. That's quantum foam. It's where the rules of physics as we know them start to break down, and where particles pop in and out of existence in a cosmic dance of uncertainty. Why does this matter? Because quantum foam isn't just a wild idea. It's a key piece of the puzzle in understanding the universe. It's where quantum mechanics and gravity collide, where black holes whisper their secrets, and where the very nature of reality might be rewritten. Scientists are obsessed with it because it could hold the answers to some of the biggest questions in physics. What is space-time made of? How did the universe begin? And what lies beyond the limits of our understanding? So, buckle up. Over the next few minutes, we're diving into 30 mind-blowing theories about quantum foam, from wormholes and multiverses to the very fabric of reality itself. By the end of this video, you'll see the universe in a whole new way, ready to explore the frothy, chaotic depths of existence. Let's go. Now, let's zoom in on the very first theory: quantum foam as the fabric of spacetime itself. Picture this: if spacetime were a sheet of paper, quantum foam would be the microscopic texture you'd see if you could magnify it 1 trillion times. At this unimaginably small scale, spacetime isn't smooth or static. It's a seething, bubbling sea of fluctuations. This is where the universe gets weird and where the rules of classical physics start to blur. This idea didn't come out of nowhere. It's the result of a cosmic tug of war between two of the most groundbreaking theories in physics: quantum mechanics and general relativity. Quantum mechanics tells us that at the tiniest scales, nothing is certain. Particles pop in and out of existence, and energy fluctuates unpredictably. General relativity, on the other hand, describes spacetime as a smooth, continuous fabric that bends and warps under the influence of gravity. But when you try to combine these two theories, things get messy. That's where quantum foam comes in. It's the bridge between these two worlds, suggesting that spacetime itself is made up of tiny, ever-changing bubbles or fluctuations. Think of it like the static on an old TV screen, except instead of random noise, it's the very fabric of reality flickering in and out of existence. These fluctuations are so small that we can't directly observe them yet. But they're there, shaping the universe at its most fundamental level. What does this mean for our understanding of reality? Well, if spacetime is made of quantum foam, it challenges the idea that the universe is a smooth, continuous place. Instead, it suggests that reality is granular, like a cosmic pixelation at the smallest scales. This could have profound implications for everything from the nature of black holes to the origins of the universe itself. So, as we peel back the layers of quantum foam, we're not just exploring the fabric of spacetime, we're redefining what it means to exist, and this is just the beginning. Next, we'll dive into how these tiny fluctuations give rise to something even stranger: virtual particles and quantum uncertainty. Stay tuned. Now, let's take a closer look at something even more mind-bending: virtual particles and their role in the quantum foam. Imagine the quantum foam as a bubbling cosmic soup, where particles don't just sit still, they pop into existence, interact, and vanish in the blink of an eye. These fleeting particles are called virtual particles, and they're not just a quirky side effect of quantum mechanics, they're a fundamental part of how the universe works. Here's the fascinating part: virtual particles aren't just random noise. they're a direct consequence of the uncertainty principle, which tells us that at the quantum level, energy can fluctuate unpredictably. These fluctuations allow pairs of particles and antiparticles to briefly emerge from the quantum foam, only to annihilate each other moments later. It's like the universe is constantly borrowing energy from nowhere, creating and destroying particles in an endless dance. But why does this matter? Well, these quantum fluctuations aren't just happening in some abstract, far-off realm, they're happening everywhere all the time. Even in the vacuum of space, which we often think of as empty, virtual particles are constantly popping in and out of existence. This means that the vacuum isn't truly empty. It's a seething, dynamic field of energy and particles, all thanks to the quantum foam. This idea is a cornerstone of quantum field theory, which describes how particles and forces interact at the most fundamental level. According to this theory, every particle we know, electrons, quarks, photons, is actually an excitation of an underlying quantum field. And these fields are constantly fluctuating, giving rise to virtual particles that influence the behavior of spacetime itself. So, what does this mean for the universe? For one, it suggests that spacetime isn't just a passive backdrop, it's an active participant in the cosmic drama. These tiny fluctuations in the quantum foam can have big effects, from shaping the properties of particles to influencing the expansion of the universe. Some scientists even speculate that virtual particles could play a role in phenomena like dark energy, the mysterious force driving the universe's accelerated expansion. As we explore the strange world of virtual particles, we're not just uncovering the quirks of quantum mechanics, we're peering into the very fabric of reality. And this is just the tip of the iceberg. Next, we'll dive into an even wilder idea, the possibility of wormholes forming within the quantum foam. Stay with us, it's about to get even more fascinating. Now, let's venture into an even more intriguing possibility: tiny wormholes hidden within the quantum foam. Picture this: the quantum foam isn't just a chaotic sea of particles and energy. It might also be a network of microscopic tunnels connecting distant points in spacetime. These hypothetical tunnels are known as wormholes, and while they sound like science fiction, they're grounded in the math of general relativity and quantum mechanics. Here's how it works. According to some theories, the intense fluctuations in the quantum foam could create incredibly small wormholes, far tinier than an atom. These wormholes wouldn't be the massive, star-spanning tunnels you see in movies. They'd be fleeting, unstable, and almost impossible to detect. But their existence could have profound implications for our understanding of the universe. One of the most exciting ideas is that these tiny wormholes might allow for faster-than-light travel, or at least the theoretical possibility of it. In theory, a wormhole could act as a shortcut through spacetime, connecting two distant locations in an instant. While we're nowhere near being able to create or stabilize such wormholes, their potential existence raises fascinating questions about the nature of spacetime and the limits of physics. This idea also ties into the broader study of wormholes, which have been a staple of theoretical physics for decades. Scientists like Albert Einstein and Nathan Rosen first proposed the concept of wormholes, often called Einstein-Rosen bridges, as solutions to the equations of general relativity. But it's the quantum foam that might provide the missing piece of the puzzle, suggesting how these wormholes could form naturally at the smallest scales of the universe. Of course, there are challenges. These quantum wormholes would be incredibly unstable, collapsing almost as quickly as they form. Some theories suggest that exotic matter with negative energy might be needed to keep them open, but such matter has never been observed. Still, the possibility of wormholes in the quantum foam opens up a world of speculation and exploration, from the nature of spacetime to the potential for interstellar travel. As we ponder these tiny tunnels in the fabric of reality, we're reminded just how strange and wondrous the universe can be, and this is just the beginning. Next, we'll explore how the quantum foam might hold the key to understanding one of the most mysterious objects in the cosmos, black holes. Stay tuned because things are about to get even more fascinating. Now, let's shift our focus to one of the most profound mysteries in the cosmos, black holes, and how the quantum foam might hold the key to understanding their entropy. Black holes are often thought of as cosmic vacuum cleaners, swallowing everything in their path, but they're also incredibly complex objects with properties that challenge our understanding of physics. One of these properties is entropy, a measure of disorder or randomness within a system. And here's where the quantum foam comes into play. Stephen Hawking, one of the greatest minds in theoretical physics, proposed that black holes aren't just empty voids, they have entropy, and a lot of it. But where does this entropy come from? That's where the quantum foam steps in. Imagine the quantum foam as a chaotic, seething sea of tiny fluctuations at the smallest scales of spacetime. These fluctuations aren't just random noise, they could be the microscopic building blocks of black hole entropy. Here's the idea: the quantum foam's structure might encode information about the particles and energy that fall into a black hole. As matter gets pulled into a black hole, it doesn't just disappear, it leaves behind a kind of footprint in the quantum foam. This footprint could be what we perceive as entropy, a record of the black hole's history and the particles it has consumed. In other words, the quantum foam might act like a cosmic hard drive, storing the information that defines a black hole's entropy. This connection between quantum foam and black hole entropy is more than just a fascinating idea. It's a potential bridge between quantum mechanics and general relativity, two of the most successful but seemingly incompatible theories in physics. Hawking's work on black hole entropy suggested that black holes emit radiation, now known as Hawking radiation, which slowly causes them to lose mass and eventually evaporate. But if black holes can evaporate, what happens to all the information they've swallowed? The quantum foam might provide the answer, suggesting that the information isn't lost but preserved in the foam's intricate structure. Of course, this is still a theoretical framework and many questions remain. How exactly does the quantum foam store this information? Can we ever observe or measure it? These are the kinds of questions that keep physicists up at night, and they highlight just how much we still have to learn about the universe. As we explore this connection between quantum foam and black hole entropy, we're reminded that even the most mysterious objects in the cosmos might have their roots in the tiniest scales of reality. And with that, we're ready to dive into another mind-bending idea: how the quantum foam might tie into the holographic principle, a theory that suggests our universe could be a two-dimensional projection. Stay with us because the mysteries only get deeper from here. Now, let's take a step into one of the most mind-bending ideas in modern physics, the holographic principle. This theory suggests that all the information in our three-dimensional universe might actually be encoded on a two-dimensional surface, like a cosmic hologram. It's a concept that challenges our everyday understanding of reality, and it's here that the quantum foam comes into play once again. The holographic principle emerged from the study of black holes and their entropy, which we just explored. Scientists realized that the amount of information a black hole can hold is proportional to its surface area, not its volume. This led to the radical idea that the universe itself might work the same way, that everything we see, feel, and experience could be a projection from a two-dimensional boundary. So, where does the quantum foam fit into this? Think of the quantum foam as the pixels of this cosmic hologram. At the smallest scales, the foam's fluctuations could represent the fundamental bits of information that make up the universe. Just like the pixels on a screen combine to create a vivid image, the quantum foam's chaotic activity might encode the data needed to project our three-dimensional reality. This idea has profound implications. If the holographic principle is correct, it means that the universe isn't as three-dimensional as it seems. Instead, it's more like a movie playing on a flat screen, with the quantum foam acting as the underlying code that generates the illusion of depth and complexity. It's a concept that blurs the line between science and philosophy, forcing us to rethink what we mean by reality. But how could this possibly work? One way to think about it is through the lens of quantum gravity. The holographic principle suggests that the quantum foam's structure might hold the key to unifying quantum mechanics and general relativity, two theories that have long resisted reconciliation. By treating spacetime as a holographic projection, physicists hope to find a deeper, more fundamental description of the universe, one that explains everything from the behavior of particles to the nature of black holes. Of course, this is still a highly speculative idea, and many questions remain. How exactly does the quantum foam encode this information? Can we ever test the holographic principle experimentally? These are the kinds of challenges that push the boundaries of science, reminding us just how much we still have to discover. As we wrap up this exploration of the holographic principle and its connection to the quantum foam, we're left with a tantalizing thought. What if the universe is far stranger than we ever imagined? And with that, we're ready to dive into another fascinating theory, how the quantum foam might be linked to dark energy, the mysterious force driving the universe's accelerated expansion. Stay tuned, because the journey into the unknown is just getting started. Now, let's shift our focus to another intriguing possibility. Could the quantum foam hold the key to understanding dark energy? Dark energy is one of the greatest mysteries in modern cosmology, the invisible force causing the universe to expand at an accelerating rate. And while its exact nature remains elusive, some scientists believe the quantum foam might offer clues to this cosmic puzzle. To understand this connection, let's revisit what we know about dark energy. It's the dominant force in the universe, making up about 68% of its total energy content. Yet, despite its overwhelming presence, we have no idea what it actually is. What we do know is that it exerts a kind of negative pressure, pushing galaxies apart faster and faster over time. But where does this energy come from? This is where the quantum foam enters the picture. At the smallest scales, the foam is a seething, chaotic sea of fluctuations, particles, and energy popping in and out of existence. These fluctuations aren't just random noise, they're a fundamental feature of spacetime itself. Some theorists propose that these tiny, rapid changes in energy could add up over vast distances, creating a kind of background energy that permeates the universe. In other words, the quantum foam might be the source of dark energy. Imagine the foam as a bubbling pot of water, with each bubble representing a tiny fluctuation. Individually, these bubbles are insignificant, but collectively, they could generate enough energy to drive the universe's expansion. It's a bit like how the hum of countless individual voices in a crowd can create a powerful, unified sound. But how does this work in practice? One idea is that the foam's fluctuations create a kind of vacuum energy, a baseline energy level that exists even in empty space. This vacuum energy could act as a constant force, pushing spacetime apart and causing the universe to expand faster and faster. If this is true, it would mean that the quantum foam isn't just a curiosity of the very small, it's shaping the fate of the entire cosmos. Of course, this is still a speculative theory, and there are challenges to overcome. For one, the predicted energy from quantum foam fluctuations is astronomically larger than what we observe as dark energy. This discrepancy, known as the vacuum catastrophe, is one of the biggest unsolved problems in physics, but it's also a reminder that the quantum foam might hold secrets we're only beginning to uncover. As we explore this connection between the quantum foam and dark energy, we're reminded of just how interconnected the universe is. From the tiniest scales to the largest, the same fundamental processes might be at work, shaping everything from the behavior of particles to the destiny of galaxies. And with that, we're ready to dive into another fascinating idea: how the quantum foam could be the foundation for a multiverse where countless parallel universes exist. Stay tuned, because the mysteries of the cosmos are far from over. Now, let's take a step into one of the most mind-bending ideas in modern physics. Could the quantum foam be the very foundation of a multiverse? The concept of a multiverse suggests that our universe might not be the only one out there. Instead, there could be countless parallel universes, each with its own unique set of physical laws and realities. And here's where the quantum foam comes into play. At the smallest scales, the quantum foam is a turbulent, ever-changing landscape of energy and particles. These fluctuations aren't just random, they're the building blocks of spacetime itself. Some scientists propose that these tiny, rapid changes could give rise to entirely new universes. Imagine the foam as a bubbling cosmic soup where each bubble represents a potential universe. When a fluctuation becomes large enough, it might pinch off from the main fabric of spacetime, creating a separate, self-contained universe. This idea ties into the concept of eternal inflation, a theory that suggests our universe is just one bubble in a vast cosmic foam. According to this model, the quantum foam's fluctuations could trigger the rapid expansion of spacetime, leading to the birth of new universes. Each of these universes would have its own unique properties, determined by the specific conditions of the fluctuation that created it. Some might have different physical constants, while others could have entirely different laws of physics. But how does this connect to the quantum foam? Think of it like this: the foam's fluctuations are like seeds, each with the potential to grow into a full-fledged universe. Over time, these seeds could sprout into their own realities, branching off from the main fabric of spacetime. This process might be happening constantly, creating an infinite web of parallel universes, each one a product of the quantum foam's chaotic nature. Of course, this is still a highly speculative theory, and there's no direct evidence for the existence of a multiverse yet. But the idea is supported by some of the most cutting-edge theories in physics, including string theory and quantum gravity. These frameworks suggest that the quantum foam isn't just a feature of our universe, it could be the canvas on which all possible universes are painted. As we explore this connection between the quantum foam and the multiverse, we're reminded of just how vast and mysterious the cosmos truly is. From the tiniest fluctuations in spacetime to the possibility of infinite parallel realities, the quantum foam continues to challenge our understanding of existence itself. And with that, we're ready to dive into another fascinating idea: how the quantum foam might influence the flow of time itself. Stay tuned, because the journey through the mysteries of the universe is far from over. Now, let's shift our focus to another intriguing possibility: how the quantum foam might influence the very fabric of time. Time, as we experience it, seems to flow steadily forward, but in the realm of quantum foam, things aren't so straightforward. At the smallest scales, where spacetime is a seething, chaotic froth, the nature of time itself becomes far more complex. One of the most fascinating ideas is that the quantum foam could play a role in time dilation, the phenomenon where time passes at different rates depending on the strength of gravity or the speed of an object. We already know that time slows down near massive objects like black holes or when traveling at speeds close to the speed of light. But what if the quantum foam adds another layer to this? Imagine the foam as a turbulent ocean with waves and ripples constantly churning. In this chaotic environment, the flow of time might not be smooth and uniform. Instead, it could fluctuate, speeding up or slowing down in response to the foam's ever-changing structure. These fluctuations could be especially pronounced in extreme gravitational fields, where the fabric of spacetime is stretched and warped to its limits. Some scientists suggest that the quantum foam's fluctuations might create tiny time bubbles, where time flows at a slightly different rate compared to the surrounding space. These bubbles could be so small that they're almost impossible to detect, but their effects might add up over vast distances or long periods. This could help explain some of the strange behaviors we observe in the universe, like the way time seems to behave differently near the event horizon of a black hole. But the implications go even deeper. If the quantum foam can influence the flow of time, it might also challenge our understanding of time as a linear, one-way process. In the foam's chaotic environment, time might not always move forward. Instead, it could loop, twist, or even reverse in certain conditions. This idea ties into theories about closed time-like curves, where time travel becomes a theoretical possibility. Of course, these ideas are still in the realm of speculation, and we're far from having definitive answers, but the connection between quantum foam and time dilation opens up a whole new set of questions about the nature of time itself. Is time a fundamental property of the universe, or is it something that emerges from the interactions of spacetime at the smallest scales? As we explore these questions, we're reminded once again of how much we still have to learn about the universe. From the tiniest fluctuations in the quantum foam to the vast mysteries of time, the cosmos continues to challenge our understanding in ways we're only beginning to grasp. And with that, we're ready to dive into another fascinating theory: how the quantum foam might be connected to the Planck scale, the very limits of our current physics. Stay tuned, because the journey through the mysteries of the universe is far from over. Now, let's zoom in even further down to the Planck scale, the smallest possible measurements in the universe. This is where the quantum foam truly comes alive, and where our understanding of physics reaches its limits. The Planck scale is named after Max Planck, the physicist who first proposed the idea of quantized energy. It's a realm so tiny that it's almost impossible to imagine distances are measured in Planck lengths, which are about 1/1,000,000,000 of a trillionth of the diameter of a single atom. At this scale, the quantum foam isn't just a concept, it's the very fabric of reality. The Planck scale is significant because it's where the effects of quantum mechanics and gravity collide. In our everyday world, gravity is a relatively weak force, but at the Planck scale, it becomes incredibly powerful. This is where spacetime itself becomes grainy, like a digital image zoomed in too far. The quantum foam, with its constant fluctuations, is thought to be the result of this granularity. It's as if spacetime is made up of tiny, indivisible pixels, and the foam is the chaotic interplay between them. But why is the Planck scale so important for understanding quantum foam? For one, it represents the frontier of our current physics. Beyond this scale, our equations break down, and we simply don't have the tools to describe what's happening. This is where the search for a theory of quantum gravity becomes critical, a framework that can unify general relativity and quantum mechanics. Without it, the quantum foam remains a mystery, a tantalizing glimpse into a world we can't yet fully comprehend. Studying the Planck scale also helps us understand the structure of the quantum foam itself. At these unimaginably small distances, the foam's fluctuations are at their most extreme. Particles and energy pop in and out of existence so rapidly that the very concept of empty space becomes meaningless. This is where the foam's chaotic nature is most apparent, and where its influence on the larger universe might originate. Some scientists even suggest that the Planck scale could hold the key to understanding the origins of the universe itself, as the conditions in the foam might resemble those of the Big Bang. Yet exploring the Planck scale is no easy task. It's far beyond the reach of our current technology, and even our most advanced theories struggle to describe it. But that hasn't stopped physicists from trying. Experiments like those at the Large Hadron Collider aim to probe the smallest scales possible, searching for clues about the nature of spacetime and the quantum foam. Meanwhile, theoretical work continues to push the boundaries of our understanding, proposing new ideas about how the foam might behave at the Planck scale. As we delve into this microscopic world, we're reminded of just how much we still have to learn. The Planck scale is a reminder that the universe is far stranger and more complex than we can imagine. And while we may not yet have all the answers, the journey to uncover them is one of the most exciting adventures in science. With that in mind, let's turn our attention to another fascinating theory: how the uncertainty principle plays out in the quantum foam, and what it means for our ability to measure and understand the universe at its smallest scales. Now let's shift our focus to one of the most intriguing aspects of quantum foam, its relationship with the uncertainty principle. This principle, a cornerstone of quantum mechanics, tells us that at the smallest scales, certain pairs of properties like position and momentum cannot be precisely measured at the same time. In the quantum foam, this uncertainty is amplified to an extreme degree, creating a chaotic and unpredictable environment where particles and energy flicker in and out of existence in the blink of an eye. Imagine trying to measure the position of a particle within the quantum foam. The very act of measurement disturbs the system, making it impossible to know both where the particle is and how fast it's moving. This isn't just a limitation of our tools, it's a fundamental property of the universe itself. In the quantum foam, this uncertainty isn't a bug, it's a feature. The foam's constant fluctuations are a direct result of this principle, with particles and energy appearing and disappearing in a dance governed by probability rather than certainty. But what does this mean for our understanding of the universe? For one, it challenges our ability to make precise predictions at the smallest scales. In the quantum foam, the rules of classical physics break down, and we're left with a world that operates on probabilities rather than certainties. This unpredictability isn't just a quirk, it's a fundamental aspect of how the universe works at its most basic level. It forces us to rethink what we mean by reality and how we define the properties of particles and energy. The uncertainty principle also has profound implications for our ability to study the quantum foam. Because we can't measure both position and momentum with perfect accuracy, we're limited in how much we can know about the foam's structure and behavior. This doesn't mean we're completely in the dark. Quantum field theory gives us powerful tools to describe these fluctuations, but it does mean that our understanding will always have a degree of uncertainty built into it. This is why the quantum foam remains such a tantalizing mystery, even as we continue to uncover its secrets. Interestingly, some scientists suggest that the uncertainty principle might actually be a clue to the deeper nature of the quantum foam. If the foam is made up of tiny, indivisible pixels of spacetime, as some theories propose, then the uncertainty we observe could be a reflection of the granularity of the universe itself. In this view, the foam isn't just chaotic, it's a window into the fundamental structure of reality, where the rules of quantum mechanics and gravity intertwine in ways we're still struggling to understand. As we explore the implications of the uncertainty principle in the quantum foam, we're reminded of just how strange and complex the universe can be. It's a world where certainty is replaced by probability, and where the very act of observation changes what we're trying to measure. Yet, despite these challenges, the uncertainty principle also offers a glimpse into the beauty and elegance of the quantum world, a world where even the smallest fluctuations can have profound implications for the cosmos as a whole. With that in mind, let's turn our attention to another fascinating theory: how quantum foam might have played a role in the Big Bang and what it could tell us about the origins of the universe. Now, let's take a step back in time, way back to the very beginning of everything. The Big Bang is often described as the moment when the universe burst into existence. But what if the seeds of that explosive event were planted by something even more fundamental? Enter quantum foam. This chaotic, fluctuating fabric of spacetime might hold the key to understanding how the universe began. Picture this: in the moments before the Big Bang, the universe was unimaginably small, compressed into a space so tiny that quantum effects dominated. Here, the quantum foam wasn't just a backdrop, it was the stage itself. The foam's constant fluctuations, driven by the uncertainty principle, could have created tiny ripples in spacetime. These ripples, though minuscule, might have been the first stirrings of structure in the universe. In other words, the quantum foam could have been the cosmic soil from which the Big Bang grew. But how exactly could these fluctuations lead to the birth of the universe? One idea is that the foam's chaotic nature allowed for random energy fluctuations to occur. In the dense, high-energy environment of the early universe, these fluctuations could have triggered a rapid expansion, setting off the Big Bang. Think of it like a spark igniting a fire. Except in this case, the spark was a tiny fluctuation in the quantum foam, and the fire was the entire universe. This theory also ties into the concept of inflation, a period of exponential expansion that occurred just after the Big Bang. Some scientists suggest that the quantum foam's fluctuations could have provided the initial conditions needed for inflation to take off. These fluctuations would have acted as seeds, growing into the large-scale structures we see today: galaxies, clusters, and even the cosmic web that stretches across the universe. What's truly fascinating is that these quantum fluctuations didn't just disappear after the Big Bang. In fact, they left behind a kind of cosmic fingerprint. The tiny variations in density and temperature that originated in the quantum foam are still visible today in the cosmic microwave background radiation, the afterglow of the Big Bang. This radiation is like a snapshot of the universe's infancy, and it provides crucial evidence for the role quantum foam might have played in shaping the cosmos. So, what does this mean for our understanding of the Big Bang? It suggests that the universe's birth wasn't a single, isolated event, but rather the result of processes deeply rooted in the quantum realm. The quantum foam, with its chaotic and unpredictable nature, might have been the catalyst that set everything in motion. It's a humbling thought that the vast, intricate universe we see today could have sprung from the tiniest fluctuations in spacetime. As we ponder the connection between quantum foam and the Big Bang, we're reminded of just how interconnected the universe is. From the smallest scales to the largest, the same fundamental principles seem to apply. And while we may never fully unravel the mysteries of the quantum foam, each discovery brings us closer to understanding the origins of everything. With that in mind, let's turn our attention to another intriguing theory: how quantum foam might influence the arrow of time, and what it could tell us about the direction of the universe's history. Now, let's shift our focus to a question that has puzzled scientists and philosophers alike: why does time move forward? This is where quantum foam enters the picture, offering a fascinating perspective on the arrow of time. At the smallest scales, the foam's chaotic fluctuations might hold clues to why time flows in one direction and not the other. To understand this, let's start with the basics. Time, as we experience it, seems to have a clear direction from past to future. But in the realm of physics, most laws are time-symmetric, meaning they work the same whether time moves forward or backward. So, why does time have a preferred direction? One theory suggests that the answer lies in the quantum foam's inherent unpredictability. The foam's constant fluctuations create a kind of microscopic chaos, which could set the stage for time's one-way flow. Imagine the quantum foam as a bubbling pot of water. Each bubble represents a tiny fluctuation in space-time. While these bubbles pop in and out of existence randomly, their collective behavior might create a kind of temporal gradient, a subtle bias that pushes time forward. This gradient could emerge from the way energy and information spread through the foam, making it statistically more likely for time to move in one direction rather than the other. Another intriguing idea ties the arrow of time to entropy, the measure of disorder in a system. According to the second law of thermodynamics, entropy always increases over time, which is why we see things like ice melting or coffee cooling. Some scientists propose that the quantum foam's fluctuations could be the microscopic source of this increase in entropy. As the foam's bubbles interact and evolve, they might create a natural tendency toward greater disorder, effectively driving time's forward march. But what about the early universe? At the moment of the Big Bang, the universe was in an incredibly ordered state with low entropy. As it expanded, entropy began to rise and time started to flow. Could the quantum foam have played a role in this process? It's possible. The foam's fluctuations might have provided the initial nudge that set entropy on its upward trajectory, giving time its direction. In this view, the arrow of time isn't just a feature of the universe, it's a consequence of the quantum foam's dynamic nature. This theory also raises an interesting question: could time ever reverse? While it's a popular idea in science fiction, the quantum foam's role in entropy makes it highly unlikely. The foam's fluctuations create a kind of temporal scaffolding that locks time into its forward flow. Even if the universe were to contract in a hypothetical big crunch, the arrow of time would likely remain unchanged, driven by the same quantum processes that set it in motion. So, what does this mean for our understanding of time? It suggests that time's direction isn't just a cosmic accident, it's deeply rooted in the fabric of reality itself. The quantum foam, with its chaotic and ever-changing nature, might be the hidden force that shapes the flow of time from the smallest scales to the largest. It's a reminder that even the most familiar aspects of our universe, like the passage of time, are governed by the strange and mysterious rules of quantum physics. As we explore the connection between quantum foam and the arrow of time, we're reminded of how much there is still to discover. The foam's influence on time is just one piece of a much larger puzzle, one that continues to challenge and inspire scientists. With that in mind, let's turn our attention to another captivating theory: how quantum foam might be linked to the search for a theory of quantum gravity, and what it could mean for our understanding of the universe's deepest mysteries. Now, let's take a closer look at one of the most ambitious goals in modern physics, unifying general relativity and quantum mechanics. This is where quantum foam steps into the spotlight, offering a potential bridge between these two seemingly incompatible frameworks. At its core, the quest for a theory of quantum gravity aims to explain how gravity operates at the smallest scales, where the rules of quantum mechanics dominate. And quantum foam, with its chaotic and fluctuating nature, might just hold the key to unlocking this mystery. To understand why this is so important, let's revisit the basics. General relativity, Einstein's groundbreaking theory, describes gravity as the curvature of spacetime caused by massive objects. It works incredibly well on large scales like planets, stars, and galaxies. On the other hand, quantum mechanics governs the behavior of particles at the tiniest scales, where phenomena like superposition and entanglement take center stage. The problem: these two theories don't play well together. When we try to apply general relativity to the quantum world or quantum mechanics to the vastness of spacetime, the math breaks down. This is where quantum foam comes in. At the Planck scale, the smallest possible scale in the universe, spacetime isn't smooth and continuous as general relativity suggests. Instead, it's a seething, turbulent sea of quantum foam, where tiny bubbles of spacetime constantly pop in and out of existence. This chaotic behavior hints at a deeper structure, one that might reconcile the smooth curvature of spacetime with the discrete, probabilistic nature of quantum mechanics. In other words, quantum foam could be the missing link that helps us understand how gravity operates in the quantum realm. One promising approach to this problem is loop quantum gravity, a theory that attempts to quantize spacetime itself. In this framework, spacetime isn't infinitely divisible, it's made up of tiny, discrete loops or atoms of spacetime. These loops are thought to form the fabric of quantum foam, creating a granular structure that could explain how gravity emerges at the quantum level. If this theory holds, it would mean that spacetime itself has a quantum nature, and the foam's fluctuations are the result of these fundamental building blocks interacting. Another intriguing idea comes from string theory. which suggests that the fundamental particles of the universe are not point-like objects but tiny, vibrating strings. These strings exist in a higher dimensional space, and their vibrations could give rise to the particles and forces we observe, including gravity. In this context, quantum foam might represent the fuzziness of spacetime at the smallest scales, where strings interact and create the fabric of reality. While string theory is still a work in progress, it offers another potential path to unifying quantum mechanics and gravity through the lens of quantum foam. But why is this unification so crucial? Beyond satisfying our curiosity, a theory of quantum gravity could revolutionize our understanding of the universe. It might explain phenomena like black holes, where the extreme gravitational forces and quantum effects collide. It could also shed light on the Big Bang, helping us understand the universe's earliest moments. And of course, it would deepen our grasp of quantum foam itself, revealing how its chaotic fluctuations shape the very fabric of reality. As we explore the connection between quantum foam and quantum gravity, we're reminded of how much there is still to uncover. The foam's role in bridging these two great theories is just one piece of a much larger puzzle, one that continues to challenge and inspire scientists. With that in mind, let's turn our attention to another fascinating theory: how quantum foam might be linked to the Casimir effect and what it could tell us about the nature of vacuum energy. Now, shifting our focus to another intriguing connection, let's explore how quantum foam might be tied to the Casimir effect, a phenomenon that seems almost magical at first glance. Imagine two uncharged metal plates placed incredibly close to each other in a vacuum. Despite the absence of any obvious force, they're drawn together. This is the Casimir effect, and it's a direct consequence of the strange behavior of quantum foam. At its heart, the Casimir effect arises from the fluctuations of the quantum vacuum. In the quantum world, empty space isn't truly empty. Instead, it's filled with a seething sea of virtual particles that pop in and out of existence, thanks to the uncertainty principle. These fleeting particles create tiny fluctuations in energy, which we refer to as quantum foam. When two plates are placed very close together, the space between them restricts the types of fluctuations that can occur, while the space outside the plates remains unrestricted. This imbalance creates a pressure difference pulling the plates together. But what does this have to do with quantum foam? Well, the foam represents the underlying structure of these vacuum fluctuations. It's the chaotic, ever-changing fabric of spacetime at the smallest scales, where particles and energy are constantly in motion. The Casimir effect gives us a tangible way to observe the influence of these fluctuations, offering a glimpse into the behavior of quantum foam itself. In a sense, the effect is like a fingerprint of the foam, revealing its presence in the vacuum of space. This connection has profound implications for our understanding of vacuum energy. According to quantum field theory, the vacuum isn't just empty, it's brimming with energy, often referred to as zero-point energy. The Casimir effect suggests that this energy isn't just a theoretical concept, it has real, measurable consequences. By studying the effect, scientists can probe the properties of vacuum energy and, by extension, the nature of quantum foam. This could help us better understand how the foam influences the universe on both the smallest and largest scales. One of the most exciting possibilities is that the Casimir effect could provide clues about the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. Some theories suggest that dark energy might be related to the energy of the quantum vacuum. If that's the case, then understanding the Casimir effect and its connection to quantum foam could bring us closer to solving one of the biggest mysteries in cosmology. As we delve deeper into the relationship between quantum foam and the Casimir effect, we're reminded of how interconnected the universe truly is. From the tiniest fluctuations in the vacuum to the vast expanse of spacetime, every piece of the puzzle matters. And with that in mind, let's turn our attention to another fascinating theory: how quantum foam might challenge our understanding of the speed of light and what it could mean for the future of physics. Now, let's take a closer look at how quantum foam might shake up one of the most fundamental constants in physics, the speed of light. At the heart of Einstein's theory of relativity is the idea that the speed of light in a vacuum is constant, a universal speed limit that nothing can surpass. But what if, at the tiniest scales, this rule isn't as absolute as we think? This is where quantum foam comes into play. Quantum foam, with its chaotic, fluctuating nature, suggests that spacetime itself might not be smooth and continuous at the smallest scales. Instead, it could be a turbulent sea of tiny bubbles or fluctuations. Some theories propose that these fluctuations could cause the speed of light to vary ever so slightly at these minuscule scales. Imagine light traveling through this frothy, uneven fabric of spacetime. It might not move in a perfectly straight line or at a perfectly constant speed. Instead, it could experience tiny deviations, almost like a boat navigating choppy waters. This idea challenges one of the cornerstones of modern physics. If the speed of light isn't perfectly constant at the quantum level, it could have profound implications for our understanding of relativity. Einstein's theory relies on the assumption that the speed of light is the same everywhere and in every direction. But if quantum foam introduces even the slightest variations, it could mean that spacetime itself behaves differently at the smallest scales than it does in the larger, smoother universe we observe. Some scientists have even suggested that these fluctuations could lead to a phenomenon called vacuum dispersion, where different wavelengths of light travel at slightly different speeds through the quantum foam. This would be a radical departure from our current understanding, where all light in a vacuum moves at the same speed regardless of its wavelength. If true, it could open up entirely new avenues for exploring the nature of spacetime and the limits of our physical laws. Of course, testing these ideas is no easy task. The scales at which quantum foam operates are far smaller than anything we can currently measure. But experiments using ultra-precise instruments, like those designed to detect gravitational waves, might one day provide clues. By studying how light and other particles behave at these extreme scales, we could uncover evidence of quantum foam's influence on the speed of light. This theory doesn't just challenge our understanding of light, it also raises questions about the very fabric of reality. If spacetime is fundamentally grainy and fluctuating, what does that mean for our perception of the universe? Could it hint at a deeper, more complex structure underlying everything we see? As we continue to explore these ideas, we're reminded that even the most well-established laws of physics might have surprises waiting for us in the quantum realm. With that in mind, let's turn our attention to another fascinating theory: how quantum foam might reshape our understanding of the nature of reality itself. Now, shifting our focus to a deeper philosophical question, let's explore how quantum foam might fundamentally alter our understanding of reality itself. At the heart of this theory lies a profound debate. Is reality continuous, like a smooth, unbroken fabric, or is it discrete, made up of tiny, indivisible pieces? Quantum foam throws this question into sharp relief, suggesting that spacetime might not be the seamless continuum we perceive it to be. At the smallest scales, quantum foam paints a picture of spacetime as a turbulent, ever-changing sea of fluctuations. These fluctuations are so tiny that they operate at the Planck scale, far beyond our current ability to observe directly. But if spacetime is indeed grainy at this level, it challenges the classical view of a smooth, continuous universe. Instead, it implies that reality might be more like a mosaic composed of countless tiny, discrete elements. This idea forces us to reconsider not just the nature of spacetime, but the very essence of existence. Think of it this way: if spacetime is continuous, then every point in the universe is infinitely divisible with no smallest unit. but if it's discrete, there's a fundamental limit to how small things can get, a kind of pixel of reality. Quantum foam leans toward the latter, suggesting that spacetime itself might have a granular structure. This granularity could mean that our perception of reality as smooth and continuous is just an illusion, a result of our inability to observe the universe at such minuscule scales. This theory doesn't just challenge our understanding of spacetime, it also raises questions about the nature of existence. If reality is fundamentally grainy, what does that mean for concepts like motion, time, and even causality? For instance, if spacetime is made up of discrete units, does motion occur in tiny, imperceptible jumps rather than as a smooth flow? And what about time? Does it tick forward in discrete steps like the frames of a movie rather than flowing continuously? These questions touch on some of the deepest mysteries in physics and philosophy. They force us to confront the possibility that our perception of reality might be incomplete, shaped by the limitations of our senses and instruments. Quantum foam suggests that the universe might be far more complex and strange than we've ever imagined, with a hidden structure that defies our everyday experience. As we grapple with these ideas, we're reminded that the nature of reality is still one of the greatest puzzles in science. Quantum foam offers a tantalizing glimpse into a world where the rules we take for granted might not apply at the smallest scales. And while we may not yet have the tools to fully explore this realm, the questions it raises continue to inspire scientists and philosophers alike. With this in mind, let's turn to another intriguing theory: how quantum foam might help us resolve one of the most perplexing problems in physics, the black hole information paradox. Now let's dive into one of the most puzzling mysteries in modern physics, the black hole information paradox, and how quantum foam might hold the key to solving it. At its core, this paradox revolves around a fundamental question: what happens to information when it falls into a black hole? According to classical physics, once something crosses a black hole's event horizon, it's gone forever, lost to the universe. But quantum mechanics tells us that information can never truly be destroyed. This contradiction has left scientists scratching their heads for decades. Here's where quantum foam enters the picture. Some theorists propose that the chaotic, fluctuating nature of spacetime at the Planck scale could provide a way for information to escape a black hole's grasp. Imagine the quantum foam as a kind of cosmic scratch pad, where information isn't lost but instead gets scrambled and encoded into the fabric of spacetime itself. This idea suggests that even as matter and energy are pulled into a black hole, their information isn't erased, it's just transformed and stored in the foam's intricate structure. One compelling theory is that quantum foam could act as a sort of backup system for the universe. As particles and energy interact with the foam, their information might be imprinted onto its fluctuations, preserving it in a way that's hidden from our current understanding. This would mean that black holes aren't the ultimate cosmic shredders we once thought they were. Instead, they might be more like cosmic recyclers, breaking down information into its most basic components and redistributing it through the quantum foam. But how could this work in practice? Some models suggest that the foam's fluctuations could create tiny loopholes in spacetime, allowing information to leak back out over time. This process might be incredibly slow and subtle, but it could explain how information is preserved without violating the laws of quantum mechanics. It's a bit like dropping a message into a turbulent ocean. While it might seem lost at first, the waves could eventually carry it back to the surface, albeit in a scrambled form. This theory doesn't just solve the information paradox, it also opens up new questions about the nature of spacetime and the universe itself. If quantum foam can store and redistribute information, what does that mean for our understanding of reality? Could the foam be a kind of cosmic memory, recording everything that happens in the universe? And if so, how might we one day decode that information? While these ideas are still speculative, they highlight the incredible potential of quantum foam to reshape our understanding of the cosmos. By bridging the gap between quantum mechanics and general relativity, the foam might not only resolve the black hole information paradox, but also reveal deeper truths about the universe's hidden structure. As we continue to explore this fascinating frontier, one thing is clear: the quantum foam is far more than just a theoretical curiosity. It could be the key to unlocking some of the universe's greatest mysteries. With that in mind, let's turn our attention to another intriguing connection: how quantum foam might leave its mark on the cosmic microwave background radiation, offering clues about the early universe. Now, let's shift our focus to another fascinating connection: how quantum foam might leave its fingerprints on the cosmic microwave background radiation, offering us a glimpse into the universe's earliest moments. The cosmic microwave background, or CMB, is often called the afterglow of the Big Bang. It's the oldest light in the universe, a snapshot of what the cosmos looked like just 380,000 years after its birth. But what if this ancient light carries subtle clues about the quantum foam that existed even earlier? Scientists have long speculated that the chaotic, fluctuating nature of quantum foam could have left tiny imprints on the CMB. These imprints, if they exist, would be incredibly faint, like whispers from the dawn of time. But detecting them could revolutionize our understanding of the universe's infancy. The idea is that the foam's fluctuations occurring at the Planck scale might have influenced the distribution of matter and energy in the early universe. These influences could have rippled outward, leaving behind patterns in the CMB that we can now search for. One way researchers are looking for these imprints is by analyzing the CMB's temperature fluctuations. These fluctuations are like a cosmic fingerprint, revealing how matter was distributed in the early universe. If quantum foam played a role in shaping these patterns, it might have introduced subtle anomalies, tiny deviations from what we'd expect based on standard cosmological models. Finding these anomalies could be the smoking gun that proves the existence of quantum foam. Another approach involves studying the polarization of the CMB. Polarization refers to the orientation of light waves, and it can carry information about the universe's earliest moments. Some theories suggest that quantum foam could have influenced the polarization patterns in ways that are distinct from other cosmic processes. By carefully mapping these patterns, scientists hope to uncover evidence of the foam's influence. Of course, detecting these imprints is no easy task. The signals we're looking for are incredibly weak, buried beneath layers of cosmic noise. It's like trying to hear a single note in a symphony of a million instruments. But advances in technology, such as more sensitive telescopes and sophisticated data analysis techniques, are bringing us closer than ever to uncovering these hidden clues. If we do find evidence of quantum foam in the CMB, it would be a monumental discovery. It would not only confirm the existence of this mysterious structure, but also provide a window into the universe's first moments. We could learn how the foam shaped the cosmos, how it influenced the formation of galaxies, and even how it might connect to other fundamental forces and particles. This search is a reminder of how interconnected the universe is, from the smallest scales of quantum foam to the vast expanse of the cosmic microwave background. It's a journey that takes us from the tiniest fluctuations of spacetime to the grandest structures in the cosmos, all in pursuit of understanding how it all began. And as we continue to explore, one thing is certain: the quantum foam holds secrets that could rewrite the story of our universe. With that in mind, let's turn to another intriguing possibility: how quantum foam might help us unravel the mystery of the vacuum catastrophe, one of the biggest unsolved problems in physics. Now let's dive into one of the most puzzling mysteries in modern physics: the vacuum catastrophe and how quantum foam might hold the key to solving it. The vacuum catastrophe, also known as the cosmological constant problem, is a glaring mismatch between what our theories predict and what we actually observe in the universe. According to quantum field theory, the vacuum of space should be teeming with energy, a result of all the virtual particles popping in and out of existence. But when scientists calculate this energy, the numbers they get are staggeringly large, so large that if they were accurate, the universe would have torn itself apart long ago. Yet, when we look at the cosmos, the observed vacuum energy is incredibly small, almost negligible. This enormous discrepancy is what physicists call the vacuum catastrophe. So, where does quantum foam come into play? Some researchers believe that the chaotic, fluctuating nature of the foam could help explain this mismatch. At the Planck scale, spacetime isn't smooth and continuous, it's a seething, turbulent sea of quantum fluctuations. These fluctuations might somehow cancel out or redistribute the vacuum energy in ways we don't yet fully understand. Imagine the foam as a kind of cosmic filter, smoothing out the energy density of the vacuum to the tiny value we observe today. If this is true, it would mean that quantum foam isn't just a curiosity, it's a fundamental part of the universe's energy balance. One intriguing idea is that the foam's structure could act as a natural regulator, preventing the vacuum energy from reaching the extreme levels predicted by theory. This could happen through a process called renormalization, where the foam's fluctuations effectively average out the energy density over large scales. Think of it like waves on the ocean. While individual waves might be chaotic and unpredictable, the overall surface of the water appears smooth and calm when viewed from a distance. Similarly, quantum foam's microscopic chaos might lead to a stable, low-energy vacuum on cosmic scales. Another possibility is that the foam's fluctuations could interact with other fundamental forces or particles in ways that reduce the vacuum energy. For example, some theories suggest that the foam might influence the behavior of dark energy, the mysterious force driving the universe's accelerated expansion. If quantum foam and dark energy are connected, it could help explain why the vacuum energy is so much smaller than expected. This would be a groundbreaking discovery, linking the smallest scales of spacetime to the largest structures in the cosmos. Of course, these ideas are still speculative, and the vacuum catastrophe remains one of the biggest unsolved problems in physics. But the potential connection to quantum foam offers a tantalizing avenue for exploration. By studying the foam's properties and how it interacts with the vacuum, scientists hope to uncover new insights into the nature of spacetime, energy, and the universe itself. It's a reminder that even the emptiest parts of space are filled with mysteries waiting to be unraveled. As we continue to probe the depths of quantum foam, we're not just exploring the fabric of spacetime, we're also searching for answers to some of the most profound questions in science. And with that, let's turn our attention to another fascinating idea: how quantum foam challenges our understanding of space itself, suggesting that the universe might be granular at its smallest scales. Now, let's shift our focus to a concept that turns our everyday understanding of space on its head: quantum foam and the nature of space itself. For centuries, we've imagined space as a smooth, continuous fabric, like an endless sheet of paper stretching across the universe. But quantum foam suggests something far more intriguing: that space might not be smooth at all. Instead, at the tiniest scales, space could be granular, like a fine-grained sand or a pixelated image. This idea challenges one of the most fundamental assumptions in physics and opens up a whole new way of thinking about the cosmos. At the heart of this theory is the Planck scale, the smallest possible size in the universe, where the rules of classical physics break down and quantum mechanics takes over. Here, spacetime isn't the calm, unbroken expanse we're used to. It's a turbulent, frothy sea of fluctuations. These fluctuations are so intense that they create a kind of foam, with tiny bubbles of spacetime constantly forming and dissolving. This granular structure suggests that space itself might be made up of discrete, indivisible units, much like how matter is made up of atoms. If this is true, it would mean that space isn't infinitely divisible. It has a smallest possible size, a fundamental graininess that defines its structure. This idea has profound implications for our understanding of the universe. For one, it challenges the notion of a smooth, continuous spacetime that underpins Einstein's theory of general relativity. Instead, it suggests that spacetime might have a kind of quantum texture, with tiny irregularities that become noticeable only at the smallest scales. These irregularities could influence everything from the behavior of particles to the way gravity works, potentially leading to new insights into the nature of reality. One of the most exciting possibilities is that this granular structure could help resolve some of the biggest puzzles in physics, like the unification of quantum mechanics and general relativity. If spacetime is granular, it might provide a natural framework for combining these two theories, offering a way to describe gravity at the quantum level. This could be the key to developing a theory of quantum gravity, one of the holy grails of modern physics. But how do we test this idea? One approach is to look for evidence of spacetime's granularity in the behavior of particles or in the fabric of the universe itself. For example, some scientists have proposed that the granular structure of space might affect the way light travels over vast distances, causing tiny distortions that could be detected with advanced telescopes. Others have suggested that high-energy cosmic rays might interact with the foam in ways that reveal its granular nature. While these experiments are still in their early stages, they offer a tantalizing glimpse into how we might one day prove that space is not as smooth as it seems. This granular view of space also raises fascinating philosophical questions. If space is made up of discrete units, does that mean the universe is fundamentally digital, like a cosmic computer? Or is there a deeper, more complex structure waiting to be discovered? These questions remind us that even the most basic aspects of reality, like the nature of space itself, are still shrouded in mystery. As we continue to explore the implications of quantum foam, we're not just redefining our understanding of space, we're also challenging the very foundations of physics. And with that, let's turn our attention to another intriguing idea: how quantum foam might influence the role of observers in shaping the behavior of the universe. Now, let's dive into a theory that blurs the line between the observer and the observed quantum foam and the role of observers. This idea takes us into one of the most debated topics in quantum mechanics. Does the act of observation itself influence the behavior of the universe? When it comes to quantum foam, this question becomes even more intriguing. Could the presence of an observer somehow affect the frothy, fluctuating nature of spacetime at the smallest scales? At the heart of this theory is the concept that quantum foam isn't just a passive backdrop to the universe, it might actively respond to the presence of observers. In quantum mechanics, the observer effect suggests that the act of measuring or observing a system can alter its state. For example, in the famous double-slit experiment, particles behave differently when they're being watched. Extending this idea to quantum foam raises the possibility that the foam's fluctuations might be influenced by observation, adding another layer of complexity to our understanding of spacetime. This idea ties into a broader debate about the role of consciousness in quantum mechanics. Some theorists propose that consciousness itself might play a fundamental role in shaping reality, suggesting that the universe requires an observer to collapse quantum possibilities into definite outcomes. If this is true, then quantum foam, as a fundamental aspect of spacetime, might also be subject to this influence. In other words, the foam's behavior could depend on whether or not it's being observed, making the observer an integral part of the cosmic fabric. But how could this work in practice? One possibility is that the act of observation introduces a kind of order into the chaotic fluctuations of quantum foam. Just as measuring a particle's position or momentum affects its state, observing spacetime at the Planck scale might stabilize or alter its frothy nature. This could mean that the universe we perceive is, in part, shaped by our own presence as observers, a mind-bending idea that challenges our understanding of reality. Of course, this theory is highly speculative and raises as many questions as it answers. For instance, what counts as an observer? Does it have to be a conscious being, or could any interaction with the environment suffice? And if observers do influence quantum foam, how far does this influence extend? These questions push the boundaries of both physics and philosophy, inviting us to rethink the relationship between the observer and the cosmos. While the idea of observers influencing quantum foam remains controversial, it highlights the deep connections between quantum mechanics, consciousness, and the nature of reality. It reminds us that the universe might not be as objective as we once thought, that our role as observers could be more significant than we ever imagined. And with that, let's turn our attention to another fascinating possibility: how quantum foam might play a role in the ultimate fate of the universe. Now, let's shift our gaze to the far future of the cosmos and explore how quantum foam might play a role in the ultimate fate of the universe. This theory takes us into the realm of cosmology, where scientists speculate about how the universe could end, and whether the frothy, fluctuating nature of spacetime at the smallest scales could influence these grand cosmic outcomes. One of the most discussed scenarios is the Big Crunch, a theory suggesting that the universe could eventually stop expanding and begin collapsing in on itself. If this were to happen, quantum foam might play a crucial role in the final moments. As the universe contracts, spacetime would become increasingly compressed, and the fluctuations of quantum foam could grow more intense. Some theorists propose that these fluctuations might trigger a kind of quantum instability, accelerating the collapse and leading to a dramatic end where the universe reverts to a singularity, a state reminiscent of the Big Bang. On the other hand, there's the heat-death scenario, where the universe continues expanding forever, gradually cooling and becoming a vast, lifeless void. In this case, quantum foam might still have a part to play. As the universe grows colder and emptier, the energy within the foam's fluctuations could become the dominant force at the smallest scales. Over unimaginable timescales, these fluctuations might lead to the formation of new structures or even spark spontaneous quantum events, potentially giving rise to new pockets of energy or matter in an otherwise lifeless cosmos. Another intriguing possibility is that quantum foam could influence the transition between these scenarios. For instance, if the universe is destined for heat death, could quantum fluctuations somehow alter its trajectory? Some speculative theories suggest that the foam's chaotic nature might allow for rare, spontaneous events that could reignite the universe, creating a new cycle of expansion and contraction. While this idea is highly speculative, it highlights the profound and unpredictable nature of quantum foam. Of course, these theories are still in the realm of speculation, and much remains unknown about the ultimate fate of the universe. But what's clear is that quantum foam, as a fundamental aspect of spacetime, could hold clues to how the cosmos evolves over trillions of years. Whether it's through influencing a big crunch, shaping the path to heat death, or even sparking a cosmic rebirth, quantum foam reminds us that the universe is far more dynamic and mysterious than we often imagine. As we ponder these possibilities, we're reminded that the story of the universe is still being written, and quantum foam might just be one of the key players in its final chapters. With that in mind, let's turn our attention to another fascinating idea: the simulation hypothesis, and how quantum foam could be evidence that our universe is a digital construct. Now let's dive into a mind-bending idea that challenges everything we think we know about reality: the simulation hypothesis and its connection to quantum foam. Could the universe we live in be a highly advanced simulation? And if so, might the strange, fluctuating nature of quantum foam be the digital pixels of this simulated reality? This theory takes us into the realm of philosophy, physics, and even science fiction, blending them into a fascinating exploration of what it means to exist. At the heart of this idea is the notion that our universe operates like a computer program, with every event, particle, and interaction being the result of underlying code. If this were true, then the smallest building blocks of reality, quantum foam, might represent the fundamental resolution of this simulation. Just as a digital image is made up of tiny pixels, the fluctuations in quantum foam could be the smallest units of information in a simulated cosmos. These fluctuations, constantly popping in and out of existence, might be the equivalent of the universe rendering itself in real time. Some theorists argue that the unpredictable nature of quantum foam aligns with how a simulation might handle processing limitations. In a simulated reality, computational resources would be finite, and the simulation might need to approximate certain details to save processing power. This could explain why particles at the quantum level behave so unpredictably. Their behavior isn't governed by strict laws, but by the computational constraints of the simulation. In other words, the foam's chaotic fluctuations might be the result of the universe filling in the gaps as it runs. But how could we ever test such a wild idea? One intriguing possibility lies in the search for glitches in the simulation. If our universe is a digital construct, there might be subtle inconsistencies or patterns in the behavior of quantum foam that reveal its simulated nature. For example, if scientists were to detect a kind of pixelation effect at the smallest scales of spacetime, it could suggest that reality is not continuous but discrete, like the pixels on a screen. While no such evidence has been found yet, the search continues, driven by the tantalizing possibility that we might one day uncover the true nature of existence. Of course, the simulation hypothesis remains highly speculative, and many scientists approach it with skepticism. However, it's a fascinating thought experiment that pushes the boundaries of our understanding. Whether or not our universe is a simulation, the idea that quantum foam could be the fabric of a digital reality invites us to question what we know about space, time, and the very nature of existence. As we ponder this extraordinary possibility, let's turn our attention to another intriguing theory: how quantum foam challenges our understanding of energy and whether it might hold the key to unlocking new forms of power at the smallest scales. Now, let's shift our focus to a theory that reimagines one of the most fundamental concepts in physics: energy. Quantum foam doesn't just challenge our understanding of space and time, it also forces us to rethink what energy really is at the smallest scales. Could energy itself be quantized, broken into discrete packets within the chaotic fluctuations of quantum foam? This idea takes us to the cutting edge of physics, where the rules we take for granted might not apply. At the heart of this theory is the idea that energy, like matter, might not be continuous but instead exists in tiny, indivisible units. In the world of quantum mechanics, we already know that particles like electrons can only occupy specific energy levels, jumping between them in discrete steps. But what if this quantization extends even further, down to the very fabric of spacetime itself? Quantum foam, with its constant fluctuations, might be the stage where energy is divided into its smallest possible units, reshaping our understanding of how energy behaves in the universe. One way to think about this is to imagine energy as a kind of currency in the quantum realm. Just as money comes in specific denominations, energy in the quantum foam might exist in fixed amounts with no in-between values allowed. This could explain why certain phenomena, like the emission of light from atoms, occur in precise bursts rather than a smooth flow. The foam's chaotic nature might be the reason energy appears to snap into these discrete levels rather than flowing freely. But what does this mean for our understanding of the universe? If energy is quantized at the smallest scales, it could have profound implications for everything from the behavior of particles to the evolution of the cosmos. For example, it might help us explain why certain physical constants, like the speed of light or Planck's constant, have the values they do. These constants could be the result of the underlying rules governing how energy is divided and distributed within the quantum foam. Some scientists have even speculated that this quantization of energy could lead to new forms of technology. If we could harness the discrete nature of energy at the quantum level, it might open the door to revolutionary energy sources or computing systems that operate on principles we can't yet imagine. While this remains speculative, the idea highlights just how much we still have to learn about the universe's most basic building blocks. As we explore this theory, it's important to remember that quantum foam is still a mystery in many ways. Its chaotic, unpredictable nature makes it incredibly difficult to study, and much of what we know is based on theoretical models rather than direct observation. Yet the possibility that energy itself might be quantized within the foam invites us to rethink some of the most fundamental assumptions in physics. With this in mind, let's turn our attention to another fascinating idea: how quantum foam represents the frontier of modern physics and what it means for the future of scientific discovery. Now, let's venture into a realm where the very limits of our understanding are tested: quantum foam as the frontier of modern physics. This theory takes us to the edge of what we know, where the rules of the universe seem to blur, and the tools we rely on to study it begin to falter. Quantum foam isn't just a curiosity, it's a challenge to the very foundations of physics, pushing us to rethink how we explore the cosmos. At the heart of this challenge is the scale at which quantum foam operates. We're talking about distances so small they're measured in units called Planck lengths, a scale so tiny that it's almost impossible to imagine. To put it in perspective, if an atom were the size of a football stadium, a Planck length would be smaller than a single grain of sand on the field. At this scale, the smooth, continuous spacetime we're familiar with breaks down, replaced by a chaotic, fluctuating foam. But here's the problem: our current technology and theories aren't equipped to study phenomena at such minuscule scales. It's like trying to read a book with a magnifying glass that only works halfway. One of the biggest hurdles is the uncertainty principle, a cornerstone of quantum mechanics. At the Planck scale, the very act of measuring something changes it, making it nearly impossible to get a clear picture of what's happening. Imagine trying to take a photograph of a hummingbird's wings in mid-flight, but every time you snap the picture, the bird moves. That's the kind of challenge physicists face when studying quantum foam. The foam's chaotic nature means that even if we could observe it directly, the information we'd gather would be fleeting and incomplete. Another challenge is the clash between quantum mechanics and general relativity, two of the most successful theories in physics. Quantum mechanics governs the behavior of particles at the smallest scales, while general relativity describes the force of gravity on cosmic scales. But when it comes to quantum foam, these two theories don't play nicely together. The foam's structure suggests that spacetime itself is quantized, which general relativity doesn't account for. This disconnect has led scientists to search for a unified theory of quantum gravity, one that can bridge the gap between these two frameworks, but so far, such a theory remains elusive. Despite these challenges, studying quantum foam could unlock some of the universe's deepest secrets. For instance, it might help us understand the nature of singularities, points of infinite density at the center of black holes. It could also shed light on the early moments of the Big Bang, when the entire universe was compressed into a space smaller than an atom. By probing the foam, we might even discover new particles or forces that operate only at these extreme scales. But what does this mean for the future of science? For one, it means we'll need new tools and technologies to explore this frontier. Current particle accelerators, like the Large Hadron Collider, are powerful, but they're not designed to probe the Planck scale. We might need entirely new approaches, such as quantum computers or advanced telescopes that can detect subtle ripples in spacetime. it also means that physicists will need to think outside the box, developing new theories and models that can account for the foam's chaotic behavior. As we stand on the edge of this uncharted territory, one thing is clear: quantum foam represents both a challenge and an opportunity. It's a reminder that the universe is far stranger and more complex than we can imagine, and that there's still so much to discover. And with that in mind, let's turn our attention to another intriguing idea: the role of mathematics in describing the enigmatic world of quantum foam. Now, let's shift our focus to a tool that has been indispensable in unraveling the mysteries of the universe: mathematics. When it comes to describing the chaotic and ever-changing nature of quantum foam, mathematics plays a crucial role. But this isn't your everyday math. We're talking about advanced equations and models that push the boundaries of what we know. The challenge lies in capturing the foam's unpredictable behavior, where space-time itself is in constant flux. How do you model something that defies the very notion of stability? That's the puzzle physicists are trying to solve. At its core, quantum foam is a dynamic system, meaning it's always changing. Traditional mathematical models are built on the assumption of smooth, continuous space-time, but quantum foam shatters that assumption. Instead of neat, predictable equations, scientists are forced to work with probabilities and uncertainties. This is where quantum mechanics comes into play, with its reliance on wave functions and probability distributions. But even these tools have their limits. The foam's chaotic nature means that small changes can lead to wildly different outcomes, making it incredibly difficult to predict or model accurately. One of the key challenges is the sheer complexity of the system. Quantum foam isn't just a single entity. It's a network of fluctuating energy and particles, each influencing the others in ways we don't fully understand. To describe this, physicists use advanced mathematical frameworks like string theory and loop quantum gravity. These theories attempt to bridge the gap between quantum mechanics and general relativity, offering new ways to think about space-time at the smallest scales. But even these frameworks are incomplete, leaving many questions unanswered. Another hurdle is the lack of experimental data. Because quantum foam operates at the Planck scale, it's nearly impossible to observe directly. This means that much of the mathematical modeling is based on theoretical predictions rather than empirical evidence. It's like trying to solve a puzzle with only half the pieces. Without concrete data, physicists have to rely on mathematical consistency and elegance to guide their theories. This has led to some fascinating ideas, such as the concept of non-commutative geometry, which suggests that space-time coordinates might not follow the usual rules of algebra at the quantum level. Despite these challenges, mathematics remains our best tool for understanding quantum foam. It allows us to explore possibilities that would otherwise be unimaginable, from the existence of extra dimensions to the behavior of space-time near singularities. And while the models we have today are far from perfect, they provide a foundation for future discoveries. As new mathematical tools and technologies emerge, we may finally unlock the secrets of this enigmatic realm. So, what does this mean for the future of physics? It means that mathematics will continue to be at the forefront of our exploration, guiding us through the complexities of quantum foam and beyond. And with that in mind, let's turn our attention to another fascinating aspect of this mysterious phenomenon: the search for new particles hidden within the foam's chaotic depths. Now let's venture into an exciting frontier of quantum foam, the possibility that it might be hiding entirely new particles. This idea isn't just science fiction. It's a serious area of research that could reshape our understanding of the universe. Quantum foam, with its chaotic and fluctuating nature, might be the perfect environment for particles we've never seen before. These particles could be the missing pieces in the puzzle of physics, helping us explain phenomena that current theories can't fully account for. So, how do scientists search for these elusive particles? One of the most powerful tools in this quest is the Large Hadron Collider, or LHC. This massive machine, located at CERN, smashes particles together at incredibly high speeds, recreating conditions similar to those just after the Big Bang. By analyzing the debris from these collisions, researchers hope to detect traces of new particles that might emerge from the quantum foam. It's like sifting through the wreckage of a cosmic explosion, looking for clues about the fundamental building blocks of reality. But why would quantum foam be a likely place to find new particles? The answer lies in its extreme energy fluctuations. At the Planck scale, the foam is a seething cauldron of energy, where particles and antiparticles pop in and out of existence. Some theorists suggest that this environment could give rise to particles that don't fit into our current models, such as supersymmetric particles or even dark matter candidates. These particles might be too heavy or too short-lived to detect under normal conditions, but the high-energy collisions in the LHC could bring them into view. Of course, the search isn't easy. Detecting new particles requires not only advanced technology but also innovative theoretical frameworks. Scientists use mathematical predictions to guide their experiments, looking for specific patterns or anomalies in the data that could signal the presence of something new. It's a bit like searching for a needle in a haystack, except the needle might not even look like a needle. It could be something entirely unexpected. What makes this search so thrilling is the potential for discovery. Finding a new particle could open up entirely new avenues of research, shedding light on questions like the nature of dark matter, the unification of fundamental forces, or even the origins of the universe itself. It's a reminder that quantum foam isn't just a theoretical curiosity, it's a window into the deepest mysteries of existence. As we continue to probe the quantum realm, the search for new particles remains one of the most exciting and challenging endeavors in modern physics. And with that, let's turn our attention to another intriguing aspect of quantum foam, how it might challenge our very understanding of cause and effect. Now, let's shift our focus to a mind-bending idea how quantum foam might upend our understanding of cause and effect. At the heart of this theory is the notion that causality, the principle that every effect has a cause, might not hold up at the smallest scales of the universe. In the chaotic, fluctuating environment of quantum foam, the rules we take for granted in our everyday world could completely break down. At the Planck scale, where quantum foam operates, space and time are no longer smooth and continuous. Instead, they're a turbulent sea of fluctuations, with particles and energy popping in and out of existence in unpredictable ways. This randomness raises a fascinating question. Can we still rely on the idea that events happen in a clear cause and effect sequence? Some theorists argue that in this realm, causality might become fuzzy or even irrelevant. Instead of one event leading directly to another, the relationship between cause and effect could become probabilistic, governed by the strange rules of quantum mechanics. This idea isn't just speculative, it has real implications for our understanding of the universe. For example, if causality breaks down at the Planck scale, it could challenge the very foundation of how we model physical processes. In our macroscopic world, we're used to thinking of time as a straight line with causes always preceding their effects. But in the quantum foam, time itself might behave differently, with events potentially influencing each other in ways that defy our conventional understanding. One intriguing possibility is that quantum foam could allow for what's known as retrocausality, where effects might precede their causes. Imagine a scenario where a particle's behavior in the present is influenced by something that happens in the future. While this sounds like science fiction, it's a serious area of study in quantum physics, with experiments exploring whether particles can sense future events and adjust their behavior accordingly. If true, this would fundamentally alter our understanding of time and causality. But why does this matter? Beyond the philosophical implications, a breakdown of causality at the Planck scale could have practical consequences for our quest to unify quantum mechanics and general relativity. If causality doesn't hold in the quantum realm, it might mean that our current theories are missing a crucial piece of the puzzle. Understanding how cause and effect operate or fail to operate in quantum foam could be the key to developing a more complete picture of the universe. As we explore this theory, it's worth remembering that quantum foam isn't just a playground for abstract ideas, it's a testing ground for the very foundations of reality. And with that, let's turn our attention to another fascinating aspect of quantum foam, the role of symmetry in shaping the universe. Now, let's take a closer look at how symmetry plays a crucial role in unraveling the mysteries of quantum foam. Symmetry in physics isn't just about balance or aesthetics, it's a fundamental principle that governs the behavior of the universe at its most basic levels. In the chaotic, ever-shifting landscape of quantum foam, symmetries might hold the key to understanding the deeper structure of reality. At its core, symmetry refers to the idea that certain properties of a system remain unchanged even when the system undergoes transformations. For example, a circle looks the same no matter how you rotate it, it's symmetrical. In the quantum foam, symmetries could dictate how particles and energy interact, how spacetime fluctuates, and even how the universe evolves over time. These symmetries aren't just abstract concepts, they're deeply embedded in the fabric of the quantum realm. One of the most intriguing aspects of symmetry in quantum foam is its connection to the laws of physics. Many of the fundamental forces and particles we know today, like electromagnetism and the Higgs boson, are understood through the lens of symmetry. In the quantum foam, these symmetries might take on new forms, revealing patterns or relationships that we haven't yet discovered. For instance, some theorists suggest that the foam's fluctuations could be governed by hidden symmetries, which might explain why particles behave the way they do at such tiny scales. But symmetry in quantum foam isn't just about particles and forces, it could also shed light on the nature of spacetime itself. If spacetime at the Planck scale is a turbulent, fluctuating sea, then symmetries might act as a kind of glue, holding everything together in a coherent way. This could mean that the symmetries we observe in our macroscopic world are just the tip of the iceberg, with deeper, more intricate symmetries operating beneath the surface. Another fascinating idea is that symmetries in quantum foam might help us bridge the gap between quantum mechanics and general relativity. These two theories, which describe the very small and the very large, are notoriously difficult to reconcile. But if symmetries in the foam can unify the behavior of particles and spacetime, they might provide a pathway to a more complete theory of everything. This would be a monumental breakthrough, offering insights into everything from black holes to the origins of the universe. As we explore the role of symmetry in quantum foam, it's worth reflecting on how these ideas challenge our understanding of reality. Symmetries aren't just mathematical curiosities, they're the building blocks of the universe, shaping everything from the tiniest particles to the vast expanse of spacetime. And with that, let's turn our attention to the final frontier of quantum foam, its potential to shape the future of cosmology. As we step into the final chapter of our exploration, let's consider how quantum foam could redefine the future of cosmology. This mysterious, ever-shifting fabric of spacetime isn't just a curiosity, it's a frontier that could unlock some of the universe's deepest secrets. From the origins of the cosmos to the fate of black holes, quantum foam might hold the answers to questions that have puzzled scientists for decades. One of the most exciting possibilities is that quantum foam could help us understand the very beginning of the universe. The Big Bang, which marked the birth of everything we know, is still shrouded in mystery. What triggered it? What existed before it? Some theorists suggest that quantum foam might have played a role in seeding the initial conditions of the universe. If we can decode the foam's structure, we might uncover clues about the universe's first moments, offering a glimpse into the ultimate origin story. But the implications don't stop there. Quantum foam could also revolutionize our understanding of black holes. these cosmic giants with their immense gravitational pull are still full of unanswered questions. How do they store information? What happens to matter that falls inside? Quantum foam might provide a framework for understanding the microscopic structure of black holes, potentially resolving long-standing puzzles like the information paradox. By studying the foam, we could gain insights into how black holes form, evolve, and eventually dissipate. Another area where quantum foam could make a huge impact is in the search for a unified theory of physics. Right now, quantum mechanics and general relativity, the two pillars of modern physics, don't play well together. Quantum foam, with its blend of quantum fluctuations and spacetime dynamics, might offer a bridge between these two theories. If we can understand how the foam operates at the Planck scale, we might finally uncover the elusive theory of quantum gravity, bringing us closer to a complete picture of the universe. Of course, there are still many questions left to answer. What exactly is the nature of quantum foam? How do its fluctuations influence the behavior of particles and spacetime? And perhaps most importantly, how can we test these ideas experimentally? While current technology limits our ability to probe the Planck scale directly, scientists are exploring indirect methods such as studying the cosmic microwave background or searching for tiny deviations in the speed of light. These efforts could bring us closer to confirming or challenging our theories about quantum foam. As we look to the future, one thing is clear: quantum foam is more than just a theoretical curiosity. It's a window into the deepest layers of reality, offering the potential for groundbreaking discoveries that could reshape our understanding of the cosmos. From the birth of the universe to the behavior of black holes, the mysteries of quantum foam are waiting to be unraveled. And as we continue to explore, who knows what incredible insights await us. The journey is far from over, and the possibilities are as vast as the universe itself. As we wrap up this journey through the 30 mind-bending theories about quantum foam, it's clear that this tiny, chaotic fabric of spacetime holds some of the universe's greatest secrets. From its role in the birth of the cosmos to its potential connection to black holes, dark energy, and even the multiverse, quantum foam challenges everything we think we know about reality. Each theory we've explored, whether it's the idea of wormholes forming within the foam, its link to the holographic principle, or its influence on the arrow of time, paints a picture of a universe far stranger and more intricate than we ever imagined. What makes quantum foam so fascinating is not just its complexity, but the way it forces us to rethink the very foundations of physics. It blurs the line between the familiar and the unknown, between the smooth, predictable universe we see and the chaotic, fluctuating reality that lies beneath. And while we've made incredible strides in understanding it, there's still so much we don't know. How does quantum foam shape the behavior of particles? Could it hold the key to unifying quantum mechanics and gravity? And what other surprises might it have in store as we continue to probe its mysteries? The beauty of quantum foam is that it reminds us how much we still have to discover. It's a reminder that the universe is full of wonders waiting to be uncovered, and that every question we answer leads to even more questions. So, as we close this chapter, I want to leave you with this. What do you think lies hidden within the quantum foam? Could it be the key to understanding the ultimate nature of reality, or is it just the beginning of an even deeper mystery? If you've enjoyed diving into these theories with me, don't forget to share your thoughts in the comments below. Which theory fascinated you the most? Do you have your own ideas about what quantum foam might reveal? And if you're hungry for more cosmic mysteries, hit that subscribe button and ring the notification bell so you never miss an exploration into the wonders of the universe. Thanks for joining me on this journey. Until next time, keep looking up and wondering what's out there.